If you guys have any questions, absolutely let me know. Okay, so today is November the 1st. So today what we're going to do is cover a quick review, do a quick review of composition of functions, a quick review of inverses. Those are sections 3.4 and 3.7 in your textbook. And so we'll look at those two sections very briefly again and review that. And then from there, we're going to move on to talking about exponential functions and do an introduction to exponential functions. We'll talk about exponential functions just as graphing them by plotting points. Certainly what an exponential function is first, and then graphing by plotting points, graphing the special exponential function f of x equals e to the x, transformations of e to the x, and then finally a couple of applications involving compound interest. So those are all things we'll be looking at today. Most students that I have found do relatively well with exponential functions because in the big scheme of things, coming out of polynomial and rational functions, that is actually not quite as difficult of a topic, I think, in general. I want to remind you also, for all of those of you who are watching this later in the evening or sometime later in the next couple of days, that you do have WebAssign homework that's due on the 8th of November. So that's a week from today. And that's sections 3.4 and 3.7 that we're going to go back and review again today. So make sure that you keep up with your WebAssign homework. And if you look at the list of WebAssign homework, we don't have that much left for the rest of the semester. We've done a good 2/3 of it already. Homework on exponential functions, I wanted to point that out. There is no homework on exponential functions on WebAssign. There are a few problems that I would like you to look at. So I am going to kind of give you an assignment on exponential functions. It'll actually be at the end of these notes. And those are problems I'm going to want you to work on at home, but those are not things that I'm going to pick up. So nothing that will be picked up on exponential functions, nothing on WebAssign, and nothing from these problems that I'm going to give you at the end of these notes. The last thing to mention is W day. Remember, that is the last day to get a W in a class. After that day, you are enrolled in the class one way or another. And the W day in this semester is November the 10th. So that's the end of next week. And so you've got these next few days, and you will get your grades for exam 2 back next week before the W day. So you'll have some information about any decisions you have to make about the class. And as I tell all of my students, my face-to-face students and my online students, that I would not make any decisions until you've talked to me about your status in class. So I would be happy to sit down and talk to you over WebEx or by email, and we can go over and talk about what your status is in the class. So please kind of take advantage of that. All right. So we want to go back and talk about composition, very briefly talk about composition and inverses. And then we'll come back to that calculator in a minute. So let's talk about composition. So a review of composition, a very quick review of composition. Now remember that composition is a way of taking a function of a function. That's one way to say it in words. It's a function of a function. All right, and the notation for composition, remember we use these open circles, and we have f. This is red, f composed with g, and the definition is that this is f of g of x. So anytime you look at f of g of x or g of f of x, you're talking about composition, function composition, or composing functions with each other. So g, circle f, g composed with f of x is defined to be g of f of x. So what you're doing is you're plugging one function into the other function. So plugging one function into the other one. All right, so let's see. Amber asked a question about WebAssign, and so that would be a good problem to look at composition. This is number 2 on WebAssign, and the function. So this is number 2, WebAssign, section 3.4. And you've got the function f of x equals x squared plus 4, and the function g of x equals the square root of x plus 7. And in WebAssign, you're asked to find f of g of x, and you're also asked to find g of f of x. Now, the notation for this, I want to remind you, sometimes you'll see it written in composition notation like this. So make sure that you know that those mean the same thing, and then the same with g of f, that this is g circle f of x, that those notations mean the same thing. They're different ways of writing the same thing. All right, so in the first one, f of g of x, so the g of x, that inside function, is the one you start with. And so you have f of the square root of x plus 7. And then that says, what are we doing? We're taking the square root of x plus 7 function, and we're substituting it into the x squared plus 4 function. So I go to f, and notice that f is x squared plus 4. So I always take the x, and I put an open set of parentheses there, and then I'm going to drop in my function. So I'm literally putting the g function into the f function like this. Right, dropping the square root of x plus 7 into the f function. And then you have the square root of x plus 7 squared. As long as x plus 7 is positive, then you're allowed to say that that's just x plus 7. And x plus 7 would have to be positive in this case. And so that's okay to write. And then you have x plus 7 plus 4, or x plus 11. And that's our composition function right there. So that would be f of g of x. All right, and then the composing the other way. Now, so what did we do in that one? We took the square root of x plus 7 function and put it into the x squared plus 4 function. And so the other composition, we're doing the opposite. We're putting the x squared plus 4 function into the x plus 7 function. So this is g of f. So this is g of x squared plus 4. Right, I just replace f of x with what it's equal to, which is x squared plus 4. And now that says go to the g function. In every place I see an x in the g function, I put an open set of parentheses for the x, like I talked about. And then we're going to put that x squared plus 4 into those parentheses like this. So we're putting the x squared plus 4 function into the square root of x plus 7 function. And then you, inside the radical there, the parentheses really aren't necessary because it's addition. And so we just can add like terms together underneath the radical, and we get the square root of x squared plus 11. Now don't forget that you cannot take the square root of those two terms there. You can only take square roots of things that are multiplied or divided, not addition or subtraction. And so I can't simplify the square root of x squared plus 11. Since that's addition, I can't touch it. I can't take the square root of each one of those separately. So let me put here, don't do this. This is not equal to the square root of x squared plus the square root of 11. Right? That's not allowed right there. So this is our composition function right here. This is g of f of x right here. All right, so Amber asked about that question, so hopefully that kind of reminds you a little bit about composition. Let's look at one more composition function, and then we're going to talk briefly about inverse functions. So let's say that we have f of x is 2x cubed plus 1, and g of x is the cube root, let's see, I want to make sure I get this right here, the cube root of x minus 1 over 2. the cube root of x squared minus 1 over 2. All right, so we're going to look at, and there's a reason why I wanted to create that function like I did here. All right, so if we look at our two compositions in this case, so I'm going to use that composition notation first of all. So you have f circle g, which is f of g of x. And then you have g circle f, which is g of f of x, like that. All right, so in the first one, we start off with that inside function, which is the cube root of x minus 1 over 2. Like that. So I put that in place of g. And now this says go to the function f, and every place I see an x, I'm going to plug in that cube root. So here's my f function right here. It's 2x cubed plus 1. But in place of that x, I'm substituting this cube root. Right, like that. So you're putting that cube root function into the cube function like this. And when you cube root, you have a cube root of an expression, and then you're cubing it. Those are processes that undo each other, and so you're left with what's underneath the radical right there, which is just x minus 1 over 2. And then the 2's divide out, and you're left with x minus 1 plus 1, and you're left with x. And that's specifically why I made this function up like I did, is because you got x as the answer, and that leads us into the next thing we want to talk about here. All right, and then you have g of f of x, and so that would be g of 2x cubed plus 1. And right, so I start off with the f function, and I replace it with 2x cubed plus 1. So I'm putting the 2x cubed plus 1 into the cube root function. And so you've got the cube root of, and then, you know, in place of the x, I put parentheses. Right, there's my cube root function, but in place of the x, I put a parentheses, and what goes in place of those parentheses is the 2x cubed plus 1. And so you end up, let's see, doing the arithmetic underneath that radical. You end up in the numerator 2x cubed plus 1 minus 1. The 1's divide out, so you have 2x cubed over 2. And so that gives you the cube root of x cubed, which is equal to x again. All right, so there's two compositions that I've created right there. And there's g circle f of x. And the reason why I wanted to bring this up, this specific example, is remember that if you have two functions, so if you have two functions where f of g of x is equal to x and g of f of x equals x, these functions are inverses. And so I did want to talk a little bit about inverses here and talk about, going back and quickly reviewing these. So these two functions right here, f and g, that I just gave you, 2x cubed plus 1 and the cube root of x minus 1 over 2, are functions that happen to be inverses of each other. That when you compose them, then it's kind of like they cancel each other out. So if you have two functions, and we'll come back to those functions in a minute, but if f and g are inverses, whoops, then it's like they cancel each other out, right, when you operate with them in composition. So f composed with g of x equals x, and g composed with f of x is equal to x. And this property is sometimes called inverse cancellation. And this property is actually going to be important to us as we get into exponential and logarithm functions, that they kind of undo each other. And this inverse cancellation also implies that the x and y values interchange, or that they switch x and y values. We talked about that. And we also talked about the idea that their graphs were symmetric around the line y equals x. All right, so we're going to look at that with an example. So the function I want to start off with, and oh yeah, and by the way, remember, before I even do this problem, remember the notation for an inverse. Let's remind everybody of that again, is that when we talk about the inverse of a function, we usually write that inverse notation right there, that we put a -1 there that looks like an exponent, but it's not, and that's just read f inverse. You read that f inverse. All right, so as an example here, let's look at this function, f of x equals 3x minus 5. All right, that's a linear function. The first thing I want to do is I want to actually find f inverse. So I want to actually create the inverse function. And so remember, what we do here to accomplish that is we actually use this idea that inverses switch x and y values. And so that's what we do to find the inverse of a function. Instead of f of x equals 3x minus 5, we write y equals 3x minus 5. And then we do what inverses do. We switch x and y values. So that's what I did at that step right there. I switched x and y values. Right? So wherever I see a y, I put an x. Wherever I see an x, I put a y. Because that's what inverses do. And then the next step, that's the inverse, but it's not in a nice form. And so the next step is you actually take the equation and you solve it for y. So in this case, I get the y by itself. So when I say solve for y, remember that another way to say that is get y by itself. That means the same thing. So in our problem, I would add 5 to both sides and then divide by 3. And I have gotten y by itself. And so that is my inverse function. This is the inverse right here. And so I would write the notation f inverse x equals x plus 5 over 3. These two functions have the property that if you went through the composition, you'd see that these two functions cancel each other out, that you have this inverse cancellation property. Right? I could do that with one example right here, with one of the compositions. If I look at f circle f inverse right here for this problem, that would be f of f inverse of x. And so that would be f of x plus 5 over 3. That's what f inverse was. So I plug that in for f inverse. And this says go to the function f. In every place I see an x, I drop in this x plus 5 over 3. So I drop in that x plus 5 over 3 in place of x. Remember, that's what f, and let me remind you again here that this expression right here comes from the fact that f is defined to be 3x minus 5. So in place of the x, I put x plus 5 over 3. And then notice in the arithmetic, the 3's divide out, and you have x plus 5 minus 5, which sure enough is equal to x. Now you have to show the composition the other way, which I'm not going to do here, but this certainly gives us a pretty good idea that we've got the right inverse function here. Remember also that they switch x and y values. They switch x and y values, so that's another thing you can look at. So for example, in this problem, I could say, let's find f of 6. I just picked 6 out of thin air. And to find f of 6, I substitute 6 into my function. And I get 18 minus 5, which is 13. So f of 6 is equal to 13. So now notice if you look at f inverse of 13, the y value we got in that first one. So I go to my function f inverse, I put in 13 for x, and I get 18 over 3, and sure enough, that's equal to 6. So what do you have here at the very end to kind of summarize there, that we found that f of 6 was equal to 13, and f inverse of 13 was equal to 6. So notice that they did switch those x and y values, which is what's supposed to happen. All right. The last thing I wanted to mention here about these two functions, so we have, let's see, we found that f of x, or not found, but we were given that f of x was 3x minus 5. And then we created f inverse, and we got f inverse was x plus 5 over 3. So if we graph those two functions on the same coordinate system, so let's make a sketch of these, and these are both lines right here. Remember, what's supposed to happen is that these two functions' graphs are supposed to be symmetric around this line y equals x. Inverse functions always have graphs that are symmetric around y equals x, which is that kind of 45-degree line right there. So let's see, we have that f of x equals 3x minus 5 is a line. It has a y-intercept at -5, like that, because it's in slope-intercept form, so it goes through 0, -5. And then it has a slope of 3. So if I keep on going over 1 and up 3, which is what I'm doing, I'm just counting up, because the rise over run is 3 over 1. So I go up 3 over 1, up 3 over 1. So up 3 over 1, up 3 over 1, up 3 over 1. Here is my line right here. All right, so there's 3x minus 5. Like that. Now if I take those points that I just got and I reverse them, right, so there's 0, -5. Here's 1, -2. Here's 2, 1. Here's 3, 4. And finally, the last one was 4, 7. Like that. If I take all those points and I reverse them, and when I say reverse them, I mean interchange the x and y values, then I have -5, 0. Here's -5, 0. Let me write that in there too. So there's -5, 0, and then I have -2, 1. There's -2, 1 right there. Then instead of 2, 1, I have 1, 2. Here's 1, 2. Instead of 3, 4, I have 4, 3. And then finally, instead of 4, 7, I have 7, 4. And there's 7, 4 right there. Right? I interchanged x and y values. And so notice what happens with the graphs. Sure enough, you get two graphs that have symmetry around that line, y equals x. So you can see that these are clearly going to be inverses of each other. All right. So we've gone through a quick review of composition, a quick review of functions that are inverses, and so now we are ready to move on to exponential functions. And so that I'm going to go ahead and start a new page, and we're going to start talking about exponential functions, a new type of function, a new category of function. And then what we will do next week is we will look at the inverse of exponential functions, which are logarithm functions, which is why we're talking about exponential logarithm functions right now, right after we get out of inverses, is because exponential logarithm functions happen to be inverses of each other. So an exponential function is a function basically that looks like this. This is b raised to the ax power, like that. When you have a function that's written in that form, when you have b raised to the ax, what separates that function from any other function we've talked about in this so far this semester is that the variable in our problem, the variable is in the exponent. And that is what makes a function exponential is that idea that you've got a variable in the exponent. You have that exponential expression like that. No functions we've talked about so far this semester have looked like that. The variable has always been part of the base, right? So, you have we've talked about linear functions, for example. Linear functions are f of x equals 3x minus 7, for example, right? The quadratic functions were second-degree polynomial functions, 2x squared minus 3x plus 6. We talked about polynomial functions in general, so degree higher than 2. Now remember, all of these are all polynomial functions, but the first two we give special names to. Right, so that was an example of a polynomial function, 5x to the fourth minus 2x cubed plus 6x minus 3. Rational functions. So these were fractions. 2x minus 3 over x squared minus 4, right? An example of a rational function. We've talked about a little bit about absolute value functions, because those were ones we looked at with transformations. So you have f of x equals absolute value of x minus 3 plus 6. We've talked a little bit about radical functions, in particular square root functions. So we've looked at things like this, f of x equals 2 times the square root of x minus 2 plus 8. Notice none of those, these are all types of functions we have talked about so far this semester. None of those have an x that's part of the exponent in an expression, right? And so this is a really different category of function when we move on to exponential functions. So exponential function might be a function like this, just something simple like 3 to the x power, right? Where you have a base, the b is the base here, and then you have the x in the exponent. So this is the kind of function that we want to talk about. And I wanted to kind of put them on the same screen with a bunch of the other kinds of functions we've talked about this semester to make sure that you kind of see that this is really different. Now, it's really simpler written than the others completely. So that's one thing that's probably good. It's not, maybe the way we write it's not quite as complicated as some of the other functions. And so what we're going to do is talk about some basic properties of this kind of function, what their graphs look like. And you're going to find that their graphs are considerably simpler than polynomial or rational functions certainly were. And then we're going to look at some applications that involve these kinds of exponential functions also. Now, when we talk about an exponential function in general, b raised to the ax power, the a and the b are real numbers. There are some restrictions here. The b value must absolutely be positive. You can't have a negative base for an exponential function, so it's always got to be positive. Also, the base cannot be equal to 1. By the way, don't confuse that. When I say that the base has got to be positive, I'm saying that you can't, this is not okay to have a function that looks like this, an exponential function like this, negative 2 raised to the x power like that. But notice that negative 2 is inside the parentheses there. But this is okay to have a function that looks like this, f of x equals the negative of 2 to the x. Because what's the base on the first one? The base is negative 2 on this one, so that's a problem. That can't happen. The base on this one, though, is positive 2. That negative sign is just saying take the negative of that. And that's actually a reflection we'll talk about a little bit later in class today. So the second one is okay. The first one is the one we're talking about, that you can't have something where you have a negative base like that. All right. So what we're going to do is we're going to start off with a function similar to the one we had at the bottom, and we're going to just sketch this graph by plotting points. So we're going to make a table of values for 2 to the x, a very simple exponential function, and actually have a look at what the graph is, or what the graph looks like, some properties of the graph. So let's see, I'll start off with x equals 0. I'm going to just literally make a table of values here. We're going to graph this the old-fashioned way. We're going to plot points. All right, so if you plot points here, I'm just substituting 0 in place of x, so you have 2 to the 0 power. And remember that when you raise something to the 0 power, you get 1. So when x is 0, y is 1. When x is 1, you get 2 to the first power, which would be 2. When x is 2, you get 2 to the second power, which would be 4. And when x is 3, you get 2 to the third power, or 8. So notice that every time the x value increases by 1, if you look at that, there is a pattern there for this particular function. And that is that the base always doubles, right? You go from 1 to 2 to 4 to 8. So the next one's going to be 16, and so on. Now we can certainly use negative x values also. Don't forget, let me write this off to the side here. Don't forget your rule for negative exponents, and that is that if you have x to the negative a power, that's 1 over x to the a power, that the negative exponent turns that into a fraction. It takes the factor to the other part of the fraction. So if I use x equals -1, that would be 2 to the -1, which would be 1 over 2. Remember, it doesn't make it negative. It takes it and turns it into a fraction. If x is -2, you have 2 to the -2, which would be 1 over 2 to the +2, or 1 over 4. And you can see how this is going to work. When x is -3, you get 2 to the -3. That's going to give you 1 over 2 to the third, or 1 over 8, and so on. So you get 1/8 when x is -3. All right, so let's have a look at this graph. Let's plot these points, see what the graph looks like. Write down the domain and the range for the graph. So when x is 0, you get 1. When x is 1, you get 2. When x is 2, you get 4. 3 gives 8 way up here. 4 would give you 16, which is off the screen. When x is -1, you get 1/2. -2 is 1/4. -3 is 1/8, which is getting really small, really close to the x-axis. And so it appears we have a graph that has this, kind of looks like this shape right here. And so we have a graph that notices a rising graph, and it's always rising. And one characteristic of an exponential function is it just continues to rise faster and faster and faster. Also notice that this graph, as you move off to the left, is just getting closer and closer to the x-axis. So you can see that this graph has a horizontal asymptote at y equals 0. In other words, the x-axis, that there's a horizontal asymptote there. The graph gets closer and closer to the x-axis, but it never gets to the x-axis. That the domain of this function is all reals. There's no breaks in this graph anywhere. It's defined for every real number. So it's much like a polynomial function in that respect. And then its range, well, it never dipped below the x-axis. And so the range is from 0 to infinity, but there's a parenthesis around the 0, because remember, that's a horizontal asymptote. The graph gets closer and closer to that horizontal asymptote, but never ever actually gets there. So our domain is -infinity to infinity. It's all reals, and the range is from 0 to infinity. This type of function, this type of graph, is sometimes called a growth curve. It's called a growth curve if you think about the way a single-celled organism multiplies. The single-celled organism first starts off with one cell, and that one cell subdivides into 2 cells. Those 2 cells each subdivide, and so you have 4 cells. Those 4 all subdivide, you have 8 cells. And so notice that exactly mimics the y values that I'm getting in this particular function. And so this is an example of what we call exponential growth. And this is sometimes called a growth curve. All right, so let's look at a couple more. Now that we've kind of gone through a problem like that, we can start getting a little bit more of an idea of how this works and maybe not have to graph quite as many points. So if we have f of x equals 5 to the x, for example, we could make a table, but I don't think we really need as many points here. We can see the same kind of thing happening. When x is 0, you get 5 to the 0, which is 1. So notice this goes through 0, 1 again. When x is 1, you have 5 to the first, which is 5. When x is negative 1, you have 5 to the negative 1, which is 1/5. And so this graph is very similar to the graph we just got. The difference is that it is a graph that rises faster. It goes through 0, 1, but instead of going through 1, 2, this one goes through 1, 5 right here. And here you have 1, 1/5, which is kind of hard to put in there, but negative 1, 1/5. And so you get this growth curve, but it's a growth curve that is a much faster rising growth curve than the first one, and it gets down to this horizontal asymptote much faster. So it's still a growth curve, it's just a faster rising growth curve. Notice that when you have a function that's written exactly in this form, b raised to the ax, just in general, that these functions, when x is 0, I'm making a little table of values here, when x is 0, these functions always go through 0, 1. And if that a value is 1, you know, if you were just talking about f of x equals just b to the x, like that, then when x is 1, the y value is always going to be b, right? So in particular, if that constant in front of the x, and we haven't looked at one where there's anything but a 1 right there, but if that constant's just a 1 there, then this kind of function is always going to go through 1b. So if you know that, you get a good idea of how this is going to work pretty quickly, and you don't have to plot a bunch of points, like 3 to the x, for example. Then what do we know? That graph goes through 0, 1. Here's 0, 1 right here, and it goes through 1, 3. And you get this growth curve, and you can make a rough sketch of a quick, decent sketch of this curve very quickly. Just goes through 0, 1, and 1, 3. So another growth curve. F of x equals 1/4 to the x. Now this one requires a little bit more looking at here. Now, it doesn't do anything different, basically, from what we just did. So it does go through 0, 1, right? If you put 0 in there for x, you certainly get 1 for y. But this graph, notice when x is 1, you get 1/4. Now, notice that this point is actually lower down than that point 0, 1. If we make our little table off to the side, you know, you get the point 0, 1, you get the point 1, 1/4. Those all seem to fit with the other. Notice with negative 1, you get 1/4 to the negative 1, which is 4. Then remember that negative 1 is an exponent, flips it. So notice you get a similar graph. The difference is that this one is a falling graph rather than a rising graph. Same basic shape, except it's falling instead of rising. This is sometimes called a decay curve, when you have a graph that's falling like that one is. So in general, you know, if you have f of x equals b raised to the x power like this, if b is bigger than 1, you get a growth curve. If the base is a number bigger than 1, you get a growth curve. And if the base is less than 1, now remember the base also has to be positive. So if the base is between 0 and 1, you have what we call a decay curve. And it's helpful to know that going into a problem that you've got either growth or decay. All right, so let's look at another example here. So let's say we have f of x is equal to 2/5 to the x. Now let's first of all talk about whether this is growth or decay. This is a function in the form b to the x power. So b to the x. But remember from the last page we've seen if b is greater than 1, you have growth. And if b is less than 1, you have decay. So in our problem, b is 2/5, which is less than 1. This should be a decay curve. Okay, so let's look at a few points here and kind of verify that this is actually what we're going to get as a decay curve. So if we make a table of values off to the side, When x is 0, y is 1. When x is 1, y is 2/5. It's just the base. When x is 2, you get 2/5 squared, which is 4 over 25. It's getting to be a smaller number. When x is -1, you have 2/5 to the -1, which is 5/2. That's getting bigger. And so that's probably enough points to give us a really good idea that we sure have a decay curve here, like we thought at the beginning. You have 0, 1. You have 1 2/5, which is a little bit less than a half. And then you have -1 5/2, which is 2.5 up here. And you get this familiar shape that we've been talking about. You get this decay curve, like this. All right. Let's look at another example. F of x equals 4/3 to the x. So in this case, the base is 4/3, which is bigger than 1, and so we think that this should be a growth curve. So that's our suspicion here, going into this problem, that base is bigger than 1, that this is going to be growth in this case. So let's see what we got. Now let's plot a few points here, see how this is working out. We've got our familiar points, first of all, that when x is 0, y is 1. And when x is 1, we get whatever the base is, which in this case is 4/3. Now, so if you go on to 2, you get 4/3 squared, which is 16 over 9. That's a bigger number than 4/3. This is getting bigger. When x is -1, you have 4/3 to the -1, which is 3/4. When x is -2, you have 4/3 to the -2. -2 there, that would be, flip it and square it, you get 9 over 16. So let's see what this graph looks like. Here you have 0, 1, and you have 1 4/3, which is 1 1/3, so maybe right about there. And then you have 2 16/9. 2 16/9 is not quite, the y value is not quite 2. So right about in here. And this middle point probably a little bit higher than it needs to be, so probably right about in here. And then at -1, you get 3/4, maybe right about in here. And then 9/16, just a little bit bigger than a half. And even though this one's pretty shallow, you're definitely getting a growth curve here. If you feel like you need another point, you could certainly always plot another point. Like I could put in x equals 3, which is 4/3 cubed, which is 64 over 27, which is sort of vaguely around 2.5, so somewhere in this vicinity. And so you can see that this graph certainly is exhibiting this behavior, but it's pretty shallow compared to some of the other graphs as far as the growth curve. So it's not a very steep growth curve, at least right around the y-axis. So notice that the bigger the base, basically the steeper the graph. So if we, hold on real quick here, and we're going to need to add in a couple of pages before we go on to our homework. So let's go ahead and get rid of that. Okay. So if we look at f of x equals 2 to the x, and f of x equals 3 to the x, and f of x equals 5 to the x, and we'll put all of these on the same graph, same coordinate system. So 2 to the x, we know goes through 0, 1, and 1, 2. Here's 2 to the x. -1 1/2 if you want that point also. And so you get this growth curve for 2 to the x. Now what about 3 to the x? Well, 3 to the x goes through 0, 1 also, but 3 to the x goes through 1, 3. And so 3 to the x is steeper. Same basic shape, but steeper. And then 5 to the x still goes through 0, 1, but now it goes through 1, 5, steeper still. And so notice you're getting growth curves for all of those, but the base is basically controlling how steep the graph is, how fast it's increasing, how fast it's rising. All right. Now, the most important exponential function that we have out there, the most important exponential function, ultimately, for applications, is an exponential function whose base is not even a rational number. It's an irrational number. It's kind of crazy that this would be the most important one, but it turns out that this is true. That the most important exponential function is this function f of x equals e to the x, where e is an irrational number. It's sort of like pi in that its decimal never terminates, never repeats, and it's approximately 2.718. And the decimal actually goes on forever, right? It never terminates, never repeats. So it's a number between 2 and 3, closer to 3. So if you think about its graph in relationship to the graphs we just sketched, f of x equals e to the x goes through 0, 1, just like all these other exponential growth curves. And it goes through 1e, which is about 2.7. So it goes through about that point right there. That would be the point 1e. This would be the point 0, 1 right here. And those 2 points right there, taken together with the fact that you know that this is a growth curve, gives you a pretty decent sketch of e to the x. E to the x goes through 0, 1, and 1e. That's a graph that I want you to know the shape of that exponential function. Definitely want you to know that. All right, now at this point, if you are going to use a calculator to look at these graphs, do you want to look at a picture of a graphing calculator here and talk about where e to the x is on your graphing calculator. So e to the x, notice, is right here on a graphing calculator. So if you're, and it's right above the ln key, and we'll talk about the ln key next week. And so to get to e to the x, what you have to do is you have to first hit the second key and then the ln key. So you have to hit second and then ln. And if you hit those 2 keys in sequence like that, then you will bring up y equals e to the x, or you'll bring up e to the x, I should say. And if you're entering it in y equals, then you're going to get y equals e to the x. All right, and so those are important keys to know when you're talking about exponential functions. And then obviously the other important key is just the exponent key right here, right? That exponentiation key. And remember, that exponentiation key is how you enter things like y equals 5 to the x, for example. You would have to enter that as y equals, well, actually, if you're going to end the y equals screen, you would have to just hit 5, first of all, and then the caret symbol, that's called the caret symbol, and then the x. Right? And that's how you'd enter 5 to the x. So on your calculator, it would look like this. All right, so those are the important keys you're talking about when you have exponential functions that we need to talk about right now. And we'll talk more about some other things that we'll need later. All right, so let's see. Let's move on to where we were talking about e to the x. So here's e to the x right here. So one thing I will want you to know is I want you to know the graph of e to the x, certainly. And I will also want you to be able to graph transformations of e to the x. So this is what I'm talking about right here. So if you have f of x equals e to the x plus 2, for example. Well, remember what that plus 2 does at the end of a function is that it's a transformation, and this is a transformation up 2. Right? It's a a vertical shift of the graph up 2. And so it's the exponential function we just sketched, but shifted up 2 units. Okay, so here's e to the x. I'm going to put it back on this coordinate system. Here's e to the x. Goes through 0, 1, and 1e. Remember, those are your two key points for sketching this growth curve. It has a horizontal asymptote on the x-axis. So what happens is that horizontal asymptote shifts up 2 units also. So it's important to draw that in so you don't cross the horizontal asymptote. So there's a horizontal asymptote here at y equals 2 because this is a shift up 2 units. And then you could literally just count up 2 for the 2 points that you just plotted. And if you move those points up 2 units, you get these 2 points. You have that horizontal asymptote. You don't cross that horizontal asymptote because the graph doesn't do that. And there's your graph for e to the x plus 2. Right? It's important to sketch in that horizontal asymptote when you're doing this. All right, so if we have f of x equals e to the x minus 3, then that function, that will be the graph of e to the x, but shifted down 3. All right, that minus 3 will shift the graph down 3 units. When you have these these vertical shifts, up or down, it's important to sketch in this horizontal asymptote. So where's the horizontal asymptote going to be? It's going to be down there at y equals negative 3. So here's your new horizontal asymptote is down here at y equals negative 3. Remember, the original graph was up here. It had a horizontal asymptote on the x-axis. It went through 0, 1, and 1e. And here was the original graph. I'm putting that as a dashed graph because this is not my final graph right here. That was e to the x. Goes through 0, 1, goes through 1e. Remember, e is about 2.7. And what are we doing? We're literally shifting that graph down 3 units. You could shift every point down 3 units. You can literally count at that point, and here's your graph. And that would be e to the x minus 3, like that. All right. Now, don't forget, so remember that what we're using here is the fact that f of x plus k and f of x minus k shift the graph up, and they shift the graph down. Also, don't forget that if you have f of x plus k like this, that you have a shift to the left. And if you have f of x minus k, you have a shift to the right. So for e to the x, if you have f of x equals e to the x plus 5, that'd be fine. E to the x plus 5. This is going to be a shift of the graph to the left 5 units. Okay, so here's e to the x. And I always like to start in with this original basic graph. So here's e to the x, goes through 0, 1, and 1e. It's this growth curve, like this. So there's e to the x. And then I take that graph and I shift it to the left 5 units. Now notice in this case, the horizontal asymptote doesn't move at all. The horizontal asymptote is still the x-axis because this is a horizontal shift. So you just count 5 units to the left. 1, 2, 3, 4, 5, like this. And here's your new graph. All right, and notice we shifted the graph back 5 units. All right. So we went back 5, literally just could count on the coordinate system and count backwards 5 units, like that. And there's our new graph in green right there. All right, f of x equals e to the x minus 4 minus 3. So what would happen here? The x minus 4 would shift the graph, the x minus 4 would shift the graph to the right 4, and then the minus 3 would shift the graph down 3, like that. So if we were going to sketch this graph, here's e to the x. Again, every time I do a transformation of e to the x, I like to put in e to the x itself. There's 0, 1, and 1e. For one thing, it helps me kind of solidify this shape in my head, that this e to the x is going through these points. There's e to the x. Then we're going to shift this graph to the right 4 and down 3. Since there's a shift down 3, this graph has the horizontal asymptote is moving. And so I would definitely sketch in that horizontal asymptote. Horizontal asymptote has been moved down 3. And so there's my horizontal asymptote. And so I literally count now 4 to the right and 3 down. Let's see. So 1, 2, 3, 4. 1, 2, 3. Right? And here's my new starting point, sort of, for this graph. That would be that point 0, 1 shifted, and then the other point would shift right here. And this would be my new graph right here. We have not been writing down the domain and range for these, but the domain for that function would still be all reals. That doesn't change. The range does change. The range would be from 3 to infinity. All right. Let's see, a couple more we need to look at here. F of x equals negative e to the x. Now don't forget that when you have if you have a graph of f of x, that negative f of x is a reflection, and it's a reflection around the x-axis. And then if you have f of negative x, that's a reflection, but that's around the y-axis. So negative e to the x, that's the first one we want to look at. So that is a reflection, in this case, around the x-axis. And so if we're going to look at this function, our e to the x function, reflected around the x-axis, once again, I would sketch in e to the x. So if I sketch in e to the x, here it goes through 0, 1, and 1e. There's e to the x. And then I literally reflect that graph around the x-axis. So here's my reflection. I flip it upside down. And here is negative e to the x. So here's e to the x right here. Here's negative e to the x right here. It's the reflection of that graph around the x-axis. All right, if we have f of x equals e to the negative x, now I'm putting a negative sign on the x value. That's this reflection right here. This is a reflection around the y-axis. So that's a reflection, and then this would be the y-axis. So reflecting around the y-axis, again, I'm going to sketch e to the x. Put in the graph of e to the x here. Goes through 0, 1, and 1e. It's my growth curve. But now I reflect that one around the y-axis. So you're flipping it, but you're flipping it left and right. And so when you flip it left and right, you get this graph. Instead of getting a growth curve, you get a decay curve. And this is e to the negative x right here. So changing the sign of that exponent literally changes a growth curve into a decay curve. Okay, so I'm going to want you to go through some function transformations. Nothing too complicated, but I'm definitely going to want you to be able to do that. All right, so to finish class today, let's briefly talk about some applications, or an application. And the application we want to look at is called compound interest. All right, so when you look at compounding interest, this is basically when you earn interest on interest. So that when you are investing money in an account and it's compounded, it means every time it's compounded, you're not only are you earning interest on what you invested, but you're also earning interest on the interest you've already earned. So you can get interest that is compounded, for example, quarterly. If it's compounded quarterly, it's 4 times a year. If it's compounded monthly, let's say, it's 12 times a year. Compounded semi-annually would be 2 times a year. There is a formula for how you can calculate how much money you have in an account that's compounded like this, and the formula looks like this. It's A equals P times 1 plus R over N to the NT, where P is the principal. That's the amount of money that you have invested. R is the annual interest rate. As a decimal. N is the number of compoundings. And T is time in years. By the way, this is a formula I will not ask you to memorize. If you are asked a question involving compound interest, I will supply you this formula on the test. It's definitely not a formula I'm going to ask that you memorize. All right, so for example, if you invest, let's say $500 in an account that's paying 2%, compounded, let's say monthly. Then, and then how much do you have after 20 years, let's say? So in this problem, if you write down what you're given the principal to be 500. That's what you're investing. The interest rate, R, is 2%, so that would be 0.02. It's compounded monthly, so N, the number of times it's compounded per year, would be 12. And then T is the time, and that would be 20. And so you're literally substituting this information, and A, by the way, is the amount you have after those T years. So this would be A equals 500 times 1 plus 0.02 divided by 12 raised to the 12 times 20 power, like that. And this would definitely, obviously, be a calculator question. You could enter that whole thing on your calculator just as it appears if you wanted to. I'll do a little bit of the bits and pieces there. First of all, 0.02 divided by 12 is 0.0016, and the 6 repeats. And then 20 times 12 is 240, like that. So this formula would become 1.0016, the 6 repeating, to the 240th power. So what you might do here is you might enter that decimal number to the 240th power, like that, and then take that answer and multiply it by 500. So that exponentiation problem, I've just got my calculator out and I'm doing that arithmetic there. I get that that's about, this is about 1.491328. and it's, that's rounded. And so you're taking that and multiplying it by 500. So you have 500 times that number. And I'm getting about $745.66. So A would be, and depending on how you rounded it, you might have, your cents might be a little bit off from what I have right there. So that would be what we have after 20 years, $745.66. All right, now another way that interest can be compounded, and this is the last thing we want to mention here, is it can be compounded continuously. Compounded continuously means it's compounded an infinite number of times per year. Infinite compoundings per year. Now that may sound great, but it really ended up not being that much better. And the formula, though, is different. The formula, when it's a continuous compounding problem, is A equals P times E. And there's our number E in this formula, raised to the RT power. So in a problem where you have interest, let's say we have our same $500 that we just invested, but we invest it at, let's say, 4% compounded continuously, then this problem becomes A equals 500 times E raised to the R, which would be 0.04. And let's say that we still have T to be 20 years, just like we were doing before. So times 20 like that. So you might first take the 0.04 and multiply it by 20. And so you get A is equal to 500 E to the 0.8 power. And that's where you'd use the exponent key in your calculator, the E key that I pointed out to you a few minutes ago. And so I would literally enter this on my calculator, 500E raised to the 0.8 power, like that. And remember to get this command on your calculator, you enter second and then ln. If you do those two things together, then you're going to, or in sequence, then you're going to get the E with the exponentiation key like that. And when I enter that, I get 1,000, so I get A to be $1,112.77. And so that's how much we'd have after 20 years in this case. All right. Now, your homework. I do have homework for you out of exponential functions, and it's actually part of your notes. I'm going to put this at the end of your notes here. I've got just some problems written up that I'd want you to work on at home. I am not going to pick these up, but I will also probably send these out as a separate document as well to everybody, maybe by email, so that everybody has access to these as well. But I'd like you, this would be a good review of what I'm going to ask you to know about exponential functions. Graphing them by plotting points. We've got a compound interest formula problem at the bottom and a compound interest formula problem at the top. And then graphing the function f of x equals e to the x and its transformations, a couple of transformations of e to the x that I've written right here, and then that would be it. All right, so not just 10 problems, and so those would be good review problems to look at. They're part of this notes. They'll be at the very end of this lecture, and then they'll also be something that I'll try to separate out as a document and send to everybody also, so they can see what I'm asking them to know about exponential functions. Okay, so that will be all we're going to do for today. Let me know if you have any questions, and I will be more than happy to help. And so for everyone, I'm happy to help you out. Remember, please come by my office. I do have office hours on tomorrow afternoon or tomorrow morning rather, from 11 to 12, and then Sunday again from 7:30 to 9, Monday from 8 to 9. So don't hesitate to come by for help. All right, have a great day. And as Doug said earlier today, go Astros.
Thanks, Professor.
All right, take care.